Welcome back to the System Design Interview Roadmap. In our previous lesson, we explored what happens when your distributed system becomes a crime scene, where individual components report healthy status, yet the entire system fails. Today, we're diving deep into the detective work required to solve those complex puzzles. This lesson, issue 132, focuses on advanced distributed system debugging techniques. It's about shifting your mindset from fixing code to reconstructing events across a vast interconnected landscape. By the end of this lesson, you will be able to identify the unique challenges of debugging distributed systems compared to monolithic applications. You'll also learn to explain the critical role of correlation IDs in tracing requests across service boundaries. Furthermore, you'll be able to describe how temporal, debugging, and state reconstruction provide insights into system failures. Finally, we'll equip you to recognize advanced observability strategies and enterprise debugging patterns that uncover elusive bugs. This isn't just theory. It's about mastering the hidden art of distributed debugging to build more resilient systems. Let's begin our investigation. When a request travels through a distributed system, it hops between many services, databases, and queues. Without a way to link all these disparate events, debugging becomes an impossible maze. This is where correlation IDs come in, acting as your digital breadcrumbs. They are unique identifiers assigned to a request at its entry point, and then propagated across every subsequent service call and log entry. Think of it like a unique case number assigned to a customer's inquiry that follows it through every department it touches. This allows you to trace a single transaction's journey from start to finish, providing a complete picture of its interactions. But it goes beyond just tracing requests. Advanced systems use multi-dimensional correlation IDs, encoding not just the request path, but also user context, feature flags, and deployment versions. Netflix, for instance, found that this approach drastically reduced their debugging time by enabling them to reconstruct not just what happened, but why a system made specific decisions. It's about building a rich context around every event. This fundamental technique transforms scattered logs into a coherent narrative of system behavior. Next, let's explore how timing plays an equally crucial role. Traditional debugging often assumes a linear, synchronous flow, but distributed systems are inherently asynchronous and concurrent. This is why temporal debugging is a game changer. Instead of debugging by service boundaries, you debug by time windows. Google's SRE teams use temporal slicing to reconstruct system state at specific moments by collecting all events that occurred within narrow time windows. This reveals emergent behaviors invisible to individual service monitoring, like race conditions that only manifest when certain events align within milliseconds. A classic example is Uber's surge pricing bug, which only appeared when 3 conditions aligned across different services within a 200 millisecond window. Individual logs showed nothing, but temporal correlation exposed the issue. Complementing this is state reconstruction, or state archaeology. When systems fail, evidence is scattered across logs, metrics, and traces. State reconstruction involves piecing together this incomplete evidence to rebuild the system's decision-making process. Stripe, for instance, reconstructs the entire decision tree for failed payments, including credit checks, fraud scores, and third-party responses to understand why a payment failed. These techniques move beyond what happened to when and why, offering a holistic view of complex failures. Now, let's look at broader strategies. Beyond correlation and temporal analysis, several advanced techniques elevate your debugging capabilities. Imagine distributed breakpoints, which capture system state across multiple services simultaneously when specific conditions are met, giving you a snapshot of a complex failure. Then there's chaos-driven debugging, where you intentionally introduce controlled failures to understand how your system behaves and to reveal debugging pathways before real failures occur. This proactive approach builds resilience. Another powerful technique is behavioral fingerprinting, This involves creating profiles of normal system operation and then using pattern recognition to identify subtle deviations that traditional metrics might miss. Think of it like a security system learning what's normal to spot anomalies. Enterprise patterns also offer valuable lessons. Slack's intermittent message delivery failures, for example, were invisible to standard monitoring. Their breakthrough came from cohort debugging, grouping failures by customer characteristics, revealing a race condition specific to enterprise customers with certain security configurations. Shopify's Black Friday delays were solved with differential debugging, comparing working and failing scenarios in real time to pinpoint the root cause. And Airbnb's booking failures, clustered geographically, were resolved by geographic correlation debugging, mapping failures to data center routing patterns. These case studies highlight the importance of thinking broadly and contextually about debugging. We've covered a lot today, shifting our perspective on how to tackle distributed system failures. We started by identifying the unique challenges of debugging these complex systems, where bugs emerge from interactions rather than isolated components. You now understand the critical role of correlation IDs as digital breadcrumbs, tracing requests and providing rich context across service boundaries. We then explored the power of temporal debugging, which focuses on time windows to uncover race conditions and other emergent behaviors, along with state reconstruction for piecing together system decisions from scattered evidence. Finally, we looked at advanced observability strategies like distributed breakpoints, chaos-driven debugging, and behavioral fingerprinting, along with real-world enterprise patterns that demonstrate how to debug by business impact, comparison, and system topology. The core takeaway is to adopt a detective's mindset. The evidence is scattered, the timeline matters, and the crime scene spans multiple locations. Your job isn't just to fix code, it's to reconstruct what really happened. To solidify your understanding, consider this. How would you design a new